Thank you everyone for coming. My name is Nakib, and I'm here with my advisor who had lots of input and guidance in this work. And today I will be talking about some of my doctoral research that involves fluid structure interaction in extreme conditions. So today I will be talking about my doctoral research. And I have split my talk into 7 main categories. First, I will introduce the main topic of my research, and I will talk about what motivated us and what has been done in that regard. Then I will state the research objectives that we put forward for ourselves, and then I will talk about methodologies that we propose to achieve those objectives. And then I will present some simple applications of our methodologies in terms of fracture and simple linear elastic material, and then in more complex case of functionally graded materials. And then I will talk about the main topic of my research, which is modeling failure of the structures under extreme hydrodynamic events. And I will also present some results in regards of failure in the structures that are subjected to explosions or explosion-induced air ballast. And then at the end, I will give you guys some takeaways of the talk, and then I will talk about where we are right now and what is the future for us. So when we think of water or oceans in general, we always think about good things, beautiful things that are calming and like seas, beaches, and all the beautiful animals. But that's not all about oceans, right? As impossible as it may sound, ocean or water in general has become one of the biggest and very dangerous source of life-threatening disasters in our life. To give you a very simple hint, these are the things that just happened last year. You see all the dates are pretty new, and if you follow the news, the most recent one is the flood in Spain, Valencia. So this is a before-after picture from satellite. And what happened in Valencia is Valencia, there is a region called Chiva, which got like a huge amount of water or rain. So think of it as like this. Normally, the amount of rain that is supposed to drop on Chiva in 1 year dropped in 8 hours. 8 hours of rain, like 1 year of rain dropping in 8 hours. So there is a dry river that drains this rain to sea, but since the amount of rain was too much, it overflowed and it flooded the entire city. But luckily, there is another river that kind of cuts out the flood towards Valencia's main or like downtown, which would be a higher disaster that had gone there. So just to give you an example of what we are looking at, these disasters are very dangerous and life-threatening. So this is one type of fluid structure interaction where the water interacts with the structure. There is another type that behaves similarly. Like computational-wise, they are very similar, but now instead of water, we have air as fluid. This is what we call air ballast structure interaction, which can generate from anything. It can be like a human error. It can be a controlled explosion in civil engineering from civil engineering perspectives, or in more extreme case of terrorism activity. So these are the events that possess lots of complex physics that treats life and economy. All these danger and life threatening brings us to our motivation. So what can we do to prevent these events? Since these events are a direct outcome of global warming, and we all know that we are at a point that we cannot prevent global warming anymore. So what me and George did was rephrase our motivation to what can we do to at least decrease its effect on human or animal life and economy. What we see it from engineering perspective, we can influence the policy making, we can design more resilient structures, or we can develop early warning system and efficient evacuation plan to at least decrease these effects. And if you are from a computational background, one way that we can do is by computationally modeling and simulating the future events and try to act accordingly. Of course, there are some challenges in simulating these events. One of the big challenges that these events have is the flow, either water or air, are highly turbulent with very big Reynolds number that requires any computational model to take into account the turbulent nature of the flow and hence to have a turbulence model. These events, these flows also have lots of free surfaces that requires us to manage carefully. And more importantly, as you saw in the videos, when the fluid hits the structure undergoes large deformation that often causes material separation, fracture, or fragmentation that needs to be handled carefully. And from more numerical point of view, there are lots of physics involved in these systems. So the coupling, we have like two different methods, two different phases, fluid and structure, but lots of physics interchanging between these two phases. So we would want to have a method that handles this data transfer and rapid dynamic very carefully and very efficiently. Of course, there are many people trying to model these types of events. One category is CFD methods, computational fluid dynamics, which are mostly focused on the fluid part of this system, where they try to model the fluid and see what's going on there, but they do not usually take into account the structural response of the system. To take the structural response of this system, there are other people who use mesh-based FSI approaches, like finite element, finite volume, and finite difference, where they also take the structural response of these systems and they kind of see how the structure deforms. But I want to draw attention that these structures undergo large deformations and they fail. So if you're using a mesh-based method, the mesh can undergo mesh entanglement, distortion, or material separation that most of the mesh-based approaches cannot address. There's a more interesting category of methods that people are usually using is particle methods. From its name, particle methods are that do not rely on meshes. Instead, they rely on particles. So basically, they discretize the domain into small points or particles, and then they solve the equations on those particles instead of mesh. So one of the main advantage of these methods is that since they do not have mesh, it means we will not see any mesh entanglement. And they are very ideal to address the large deformations in the structure. And it becomes way easier to handle the material distortion, separation, or failure and fragmentation. So one of the very famous particle methods that you may have heard of is smoothed particle hydrodynamics, which is one of the very oldest, and it has been applied to many different scenarios in many different physics. It's truly mesh-free, and it has been successfully applied in then various industries, from aerospace to astronomy. But one thing that SPH lacks right now is that it cannot solve for fracture and fragmentation. So this brings us to our overall research objective. We eventually want to develop a model that is capable of predicting the extreme hydrodynamic events and the material failure in them. And also another model that can predict the air ballast structure, the behavior of air ballast structure interaction. But to do this, we have divided our main objectives into smaller subsets. Since SPH is not capable of modeling fracture, first we wanted to develop a comprehensive fracture model for SPH. But that's not enough, right? Like these scenarios are very extreme and very violent in nature. So after developing the fracture, we would also want to make sure that this fracture model is able to predict the structural response within extreme conditions. So this was our second objective, to test our model in that condition. And then we arrived to our main objective, one of the main objectives, which is to develop a FSI model, which is capable of efficient data transfer, which is capable of modeling the turbulent in the flow and the free surfaces, but most importantly, capable of handling large structural deformation, fragmentation, and failure. And our last, well, one before the last objective is to develop a model that is also able to predict the failure of structures in air ballast. And the last one, which is not the main objective, but it is good to have it, to make all these codes available for people to use in their work. So these are the main research objectives that we have. For all these objectives, I'm going to use three main computational methods: smoothed particle hydrodynamics, or shortly as SPH, phase field, and isogeometric analysis. I will use the first two to I will use this first to model fracturing structures, and then to model extreme fluid structure interaction that is also capable of modeling fracture. All three to model the structural failure and air ballast structure interaction scenarios. But to give you a very simple overview of what SPH is, SPH is basically a particle method that discretizes a domain, a physical domain, into small particles. And each particle has its own support domain, other particles that support the particle in terms of information, which is also called the kernel support. And if you want to, for example, evaluate the value of a function on a specific particle or position in the domain, you basically use kernel summation over the neighboring particles or the support domain. And if you want to evaluate the derivative of the function, you still do a kernel summation over the neighborhood. Instead of like applying derivative over the function itself, then you apply it over the kernel function, which is a very which can be a very well-established function, mathematical function. So this is a general idea of SPH. However, I want to draw attention to the fact that there is no term in the basic equations of SPH that would account for the structural deformation or like an interface. So if you imagine a domain that has like a crack which propagates throughout the domain, let's say this one, and if you want to make sure that SPH accounts for this crack, what traditionally you would have to do is you would explicitly track this interface and then make sure that the particles within the support domain that falls at the other side of the interface is excluded from the summation. So when you say it is kind of easy, but computationally it's very expensive and hard, because now you have to explicitly track down the surface or the interface that is going on here in every step of your simulation. So instead, since this is a very computationally heavy and costly, we suggest another method, which we call it as phase fill, which is named as phase fill. So basically, phase fill, now instead of tracking down the discontinuity itself, phase fill numerically changes the discontinuity surface into a field variable, which in our case we call it as S. So if you have a discontinuity, you don't track the surface. Instead, you have a field variable that makes sure where the surface is. Now, in case of fracture, this discontinuity is represented through this, which is based on Griffith's theory of brittle fracture, a very well-established theory. And in our case, we use a special type of phase fill that is compatible with SPH and particle methods in general, and also with explicit time integration. So in general, if you want to solve a domain for its deformation and fracture, what you would have to do is solve these two equations. The first one is for the momentum balance, and the second one is for the diffusion of the phase fill variable. Just a simple note that in this method, you don't have to track down the discontinuity surface. You don't have to give any input to how the fracture happened, when it happened, or when it branches into many. So it's a very convenient method, especially in numerical applications to be used. Now, from SPH part, these two equations can be represented as following, where you have a summation over the neighborhood. And here, this P is the first geometrical distance for the structure that can be evaluated through any constitutive model. In our case, we use Newhookians. And this is what you have to do to get the fracture evolution within a simple structure. Now, there are some cases, it doesn't happen all the time, but it's like rarely happens. The particles that are exactly located on the surface of fracture, on the surface of crack, since they are like fracture surface, they act like a dust in a very common terms. A dust is something that flies around and like there is no force to restrict them to something, like as you see in these pictures. These, of course, does not change the physics of the problem, but numerically they are inconvenient when you want to handle different physics and complex scenarios. And what we came up with was like, we need to solve this. This doesn't change the physics, but it's a problem for us. So we came up with a simple correction that we name it as omega correction, where you would apply it and the dust particles are now stuck at the surface and you don't have any flying particles around, which is convenient. So this was our fracture model. We wanted to see if this fracture model is good enough to solve any fracture. Here, what you see is a very simple tensile case where the material is pulled from two parts and there is a pre-existing crack. Then it evolves into this and then branches into two. And this is a very common benchmark that people use in fracture mechanics. And as you see, the results are quite in good agreement with the literature. Also, there is this one, which is also kind of common, but with more complex geometry. Here we have like random holes placed in the domain, and we have a pre-existing crack. And when you apply a 3-point bending force, it cracks like this. And this is the comparison between experiments and other numerical methods, and you see how good the fracture surface is. Then we moved on to apply it to more complex cases. Here are some others that still have good agreement with literature. And you see this one is an experiment, and we were able to capture very fine details of the experiment. So far we have a fracture model that can handle the fracture in simple isotropic linear elastic materials, but we are still unsure if it can handle scenarios with very extreme conditions. To test that, we applied that to a different material, which is called functionally graded materials. Functionally graded materials are an advanced type of composite materials that are usually used in aerospace and marine engineering. They have very convenient material properties. We tested our method on those, and as you see, the results are quite in good agreement with what people in literature have seen. So far, what we did is we developed a comprehensive fracture model, and we tested it on extreme conditions. Our next objective is to develop a FSI model that is capable of all these three: turbulence, data transfer, efficient data transfer, free surface, and damage in structure. Of course, when it comes to fluid-structure interaction, things get a little bit more complicated. Now we have, like, on top of having a good structural model, we also should make sure that we have a good and efficient fluid model. And more importantly, we need to make sure that our interaction, our numerical interaction between fluid and structure is very efficient and very accurate so that we don't lose any physics there. So basically, if you want to model just a fluid domain without anything in it, maybe a simple stationary wall and a simple moving object in it, what you would do in SPH is to use this two equations, one for balance of mass and then for balance of momentum, in which in balance of momentum, the first term comes from the pressure of the fluid, the second term is viscous forces, and we included the last one to account for turbulence using large eddy simulation. Now, this is what you would do to simply model a common fluid domain. Now, when it comes to also modeling the structural response in terms of fracture, things get more complicated. Now you have to also account for structure, but more importantly, you need to make sure that the communication is well established and highly efficient. So for communication, here, normally what people in literature do is they would include another extra term in this equation to make sure that the structural response is accounted within the fluid. But this gets difficult and impossible for us because now we don't only have the deformation of the fluid, but we also have another physics, which is the fracture. Including that within this term is highly difficult and sometimes impossible. So instead of including a term within the physics of the equations, what we did was, instead of coupling the physics of the two phases, what we did was we coupled the geometry of the two phases. So what I mean by geometry is we simply have a domain which has fluid and which has a structure object. And what we did was we cloned this geometry and we solved all the structural equations on top of the cloned geometry, and then we established a mapping method based on the Lagrangian polynomials to exchange pressure from the main geometry to the cloned one, and back to exchange the position and velocity from the cloned one to the main geometry. So this kind of gives us since the domains, the geometries are different, we can use any particle resolution, you can use any method on this cloned geometry, and you just have to map back the velocity and positions. So this will give you the chance to increase the accuracy of this model, to increase the accuracy of the structures without causing any computational cost on the main fluid solver. So basically, to give you our overall idea of what our algorithm looks like, we solve for the fluid domain. We map the fluid's pressure on the clone geometry. We solve for the clone geometry in terms of fracture, deformation, or any other physics that you want. You could also solve temperature without even getting involved within the fluid solver. Then you would map back the field variables to the main geometry, and then you continue your time. So we first applied our method on simple structures. This is like a free oscillating beam under a very simple initial velocity, which you can see is very, we are tracking down the tip displacement, and you see how the tip displacement is in good agreement with analytical solution. And here is a drop oscillating under a centrifugal force, and you see how the predicted results are in good agreement with analytical ones. After this, we moved on to apply our method into a more complex case. At the top, you see a channel that has an inflow of water, and there is a turbulent or a eddy forming at the back where it's facing a step. And here you see a tank full of water that applies hydrostatic pressure on the floor, and this one is the oscillation of the jumping of the floor, and as you see, it approaches to the analytical solution when the water gets stilled. So these were a little bit more complex case, but still not enough. So what we did later was applied this method into different scenarios. This one is just like impact of water on an obstacle, and these two is when the tank ruptures the tank floor, and then the water flows out of the tank. And you see the results, the predicted results are in good agreement with what we have in literature. After this, we applied our model into more complex case. Here you see that a dam breaks and hits a structure in its path, and the structure breaks down and falls apart. And here you see a water channel with the water flows and breaks the gate. So these are complicated cases. And the last one, we are like a dam breaks, and it's supposedly a building-like structure, and how the building fails in it. So these are like the capabilities of our model that is able to predict the failure on the structure and then the behavior of fluid. Now, so far, we had already done this too. Now we have a model that is capable of good data transfer, turbulent modeling, and large structural deformation modeling. And now we move on to developing a model for explosive induced air ballast structures. When it comes to explosion-induced air ballast structure, things are a little bit different than fluid structure interaction or water structure interaction. Now imagine a container that has a very complex geometry, as you see here. If our fluid was water, we would just have like water at the portion of it, and the rest would be empty. From computational point of view, we wouldn't have to solve for the rest of the geometry if we had water here. We would be just solving the water portion. In case of air, the container is always full of air, no matter what you do. So it is convenient to use Lagrangian methods for modeling water, and then Eulerian methods for modeling air. Now, for our air section, we choose isogeometric analysis to model the air. There are many reasons for that. One is that isogeometric analysis, or IGA, is a higher accurate and also models the geometry very perfectly. If you are familiar with the finite element method, isogeometric analysis is very similar to finite element method, but in finite element, we have shape functions as polynomials, as Lagrangian polynomials. In isogeometric analysis, we have B-splines. We have splines in general, but we use B-splines. So this is what we would do for a normal domain that has air in it to use to model the behavior of air. We would solve this equation, which is a basic Navier-Stokes equation. Now, when it comes to a structure inside an air container, things get complicated. Now, in the Eulerian method, traditionally, we are supposed to explicitly track down this interface between the structure and the fluid region, and then solve for it. However, like tracking any type of discontinuity is very hard and very computationally costly. So instead, we made use of another method, which is called volumetric coupling. So in volumetric coupling, instead of tracking down the surface of the interface of the two phase, we would just penalize the velocity of each phase related to each other and include it as a last term as an extra term in the governing equations. So that was our numerical method, and these are some examples. Here you see an experiment which was done back in the time. The experiment is like there is a tunnel, there is an explosion happening at the beginning of the tunnel, then the explosion wave kind of moves towards this panel, which is elastic, and then the panel kind of oscillates like this. And these are the experimental data. And this one is like the pressure value at some part on the wall of the channel. So as you see, the numerical predictions that we have with our model is kind of very similar to what people observed in experiment. This is also another similar case where now the explosion travels towards the channel, but then the channel has deformable wall. This explosion wave kind of pushes two wall to the two side. These are some extra cases. Now there is an explosion happening inside a chamber, and there is a plastic object that is subjected to explosion wave, and then the plastic object undergoes horizontal transition as well as plastic deformation at the tips. And this is the comparison of our predictions with literature, and they are in a very good shape. And these are the pressure values at different parts of these chamber. And as you see, the pressure values are also in good agreements with what other people have reported. Now, those were for normal structural deformation and plastic deformation and translation. Here, we have a brittle panel, a brittle chamber that is subjected to internal explosion. And then this explosion kind of breaks apart the chamber and it makes it travel towards many directions into many pieces. And this is where the explosion kind of breaks down a structure within the chamber. So far, we have already done all our objectives. But one thing that I kind of didn't mention here was for all the simulations that you saw, I simply assumed that the material that we are using is either metal or simple elastic isotropic material, which is not the case in normal life and in physical life. There are very complicated materials like concrete, for example. If you have a building subjected to explosion or to a water impact, then we need to have a model to accurately predict the behavior of concretes. Now, we haven't done that so far, but one of our future objective is to make sure we are accounting for good response of concrete. And the way we would do it is by using a microplane model, which is one of the models that highly accurately predicts concrete behavior. And then our last objective, but not least, in the future, we would want to make these codes and algorithms open source so other people can use it in their research. So these are some preliminary results that we have for the concrete modeling. Here we have a short concrete block subjected to compression, and here we have a long one, and here is a dog bone specimen that is under tensile loads, and you see how the predicted results by SPH is similar to the ones that the experiments have reported. So these were what we did, and this was at the beginning of May when I prepared like a timetable. Now we are here, and I was still not done the first task, which is to develop the microplane model based on GPU accelerated code. But I'm hoping to finish it soon so that George graduates me. And then we would also want to make all these codes open source for others. And then once it's open source and efficient, we would want to apply it to large scale simulations and try to report the findings. I'm not going to do the experimental one because I'm not good at it. So my groupmate colleague, she might do it later. And these are some references for you. And thank you very much for coming. Any questions?
Thank you for the good talk. I have a question about the efficiency of this method that you introduced. So in comparison with CFD and the FSI that we do with CFD, how efficient is that for large scale problems like flow in the rivers and this kind of? Because you need to solve the equation for all the particles, maybe at turbulence.
Well, the difference between computational fluid dynamics and fluid mechanics is that for fluid dynamics, we are looking at the big picture. We just are trying to see how the fluid is moving and how it has the structure surrounding it. So we are not going into details of the flow, like are we, for example, trying to measure the mechanics of a point of fluid inside the flow? Or are we trying to, for example, see if the structure is moving, or if it moves, would it fracture, and what type of stresses you will see within the flow and within the structure? So in fluid dynamics, I'm not very familiar with it, but what I know is that they don't account for that. But in fluid mechanics, they go into very details of the mechanics of the fluid, where you have to solve, you would solve for stresses, you would solve for fracture within the structure and the stress. So these means like more computations, more cost, right? So in general, what I would say is fluid dynamics is more cheaper than what we do here, but it depends on what you're looking at, right? So if people want to look at the fracture, then they have to pay a price.
I have another question. So you said for large deformation, SPH is a better method.
Particle methods in general.
Yeah. So I want to know how big should that deformation should be. For example, if I want to measure the blades deformation for a wind turbine, is that a good method or not?
Well, so I want to just like mention this. there is this problem with mesh-based methods, which we call it as mesh entanglement. So if you deform your structure or like bend it, or something happens within the structure and your mesh points, your nodes, mesh nodes, flips around, it makes a distortion of the mesh, which is a numerical inconvenience. And like the mesh-based approach, they have problems with that. Now, particles approach, no matter how much deformation you apply, since it's just one particle, they don't go this entanglement. But a question of accuracy for large deformation is more on the constitutive model rather than the SPH method itself. Like there are linear elastic constitutive model, which thinks of your structure linear elasticity. For that, your deformation, if it gets larger, you will have error in the solution. There are, for that, like people use hyperelastic models. So there is no restriction on like how large your domain could deform, but the restriction comes from the constitutive model, like what type of constitutive model you're using.
I'm not your major, but I'm curious. The model you are using is plastic and metal. So there are thousands of different plastic materials in our lives. So what kind of partners of that model? Some plastics are really robust, and some plastics are really easy to fracture. So there are different kind of plastic or materials.
Yeah. So like what we use here was a simple strain hardening material. It was very simple. It was like we have a linear region and then we have a hardening region, which is also linear. We didn't really apply complicated material models, but it can be applicable since my focus was more into development of the method rather than the constitutive model itself. Yeah, you this one, right? Yeah. So this is just a simple linear elastic plastic material that is strain hardening. So I didn't go into very like detailed modeling of plasticity because it was not my expertise area. But it depends on constitutive model. If you use a good constitutive model, you will have that material here as well.
And I have a following question: is the application? If you get the result of the simulation, what's the benefit? Like you said, in motivation, you want to reduce the cost of the human lives and the economy.
Yeah.
So if you got the simulation result, but the disaster already happened.
So yeah, these continue.
Yeah. What's the benefit of the simulation?
So these are actually like made up scenario that what happens if this thing happens, right? You can, for example, like I don't work on the disaster part, but if you have a data of, let's say, 100 years of old disaster data, and you can predict that, okay, in the next 100 years, this will happen. And if you just make that scenario within your computational domain, and then try to predict the structural response according to that. For example, if you are building a hospital, and you want your hospital to last for 200 years, right? And maybe for the next 50 years, you don't get that much of like disastrous or flood effects on the hospital, but there's one chance that there would be a scenario that will hit the hospital, and you would want to simulate that and predict the behavior of hospital. And if you see, like, for example, your hospital building is failing, then maybe you can change the material that traditionally is being used to build the hospital. You would change it to something else to make it more resilient.
Yeah.
It's more the design part.
So following a little bit on that question, I was wondering if, so when people want to use this method, for anything, would they have to be, I don't know, engineers or like programmers, like in order to use it, or like, how do you imagine that, like, I don't know, it could be incorporated into like, I don't know, software, something like simpler, or do they have to know how to code or things like that, like, in order to use that?
Actually, like nowadays, what I'm trying to do is to embed this into open source software. But the question whether they need to be an engineer or not, I think for a person who is not an engineer, it will be hard to try to like change the model in a way predicts the future, right? But for coding part, if I was able to embed it in the open source, you wouldn't have to code it. You would just like change the geometry and then it will solve it itself. Thank you for coming, everyone.